Hello, my name is Ahmet Utku Özçelik and this is my project video for Physics 101 lab. In this experiment, I compared the series and parallel configurations using Hooke's law. The objective was to observe how the effective spring constant changes depending on the configuration. Let me walk you through the process, the results and the physics behind it. For the individual spring measurement, I attached one dynamometer to the stand and recorded its equilibrium position. Then I hung weights of varying masses and measured the displacement for each weight. Each force was calculated as F equals mg, where g is the gravitational acceleration 9.8 meters per second square. By plotting force against displacement, I determined the spring constant for the single dynamometer to be 44.78 newtons per meter, which showed a 10% error compared to the expected value of 50 newtons per meter. Next, I repeated the process for the series configuration. I attached two dynamometers hand to hand and measured the total displacement for the same set of weights. In this configuration, the dynamometers shared the displacement, resulting in an effective spring constant of 23.73 newtons per meter. This value was determined by plotting a graph of force versus displacement, and the spring constant was obtained from the slope of the graph. The results showed a 5% error compared to the expected value of 25 newtons per meter. Finally, for the parallel configuration, I attached two dynamometers side by side. In this setup, the load was shared between the two dynamometers, leading to a smaller displacement. To make the displacements easier to measure, I used a different set of weights. The calculated spring constant was 104.39 newtons per meter, obtained by plotting a graph of force versus displacement and calculating the slope. The results showed a 4.4% error compared to the expected value of 100 newtons per meter. The results confirmed the theoretical predictions of Hooke's law. In the series configuration, the effective spring constant decreased compared to the individual spring, as the displacement was distributed across both springs. Conversely, in parallel configuration, the spring constant increased because the load was shared between the springs, resulting in less displacement. The graphs of force versus displacement show clear linearity, consistent with the Hooke's law where F equals kx. The slope of these graphs gave the spring constants, and comparing the slopes confirmed the theoretical relationships for series and parallel configurations. Although the results align with the theoretical values, there were some small errors. These could be attributed to manual measurement inaccuracies and the friction in the setup. Additionally, the mass of the springs themselves was neglected in the calculations. To improve accuracy, digital sensors could be used for displacement measurement, and the setup could be refined to reduce friction. These changes would make the results even more precise. The physics of this experiment revolves around the Hooke's law, which states the force exerted by a spring is proportional to its displacement, with the proportionality constant being the spring constant K. For series configurations, the effective spring constant is calculated using this formula. This results in a lower effective spring constant, meaning the system deforms more under the same load. In parallel configurations, the effective spring constant is the sum of the individual spring constants. This increases the system's stiffness and reduces the deformation under the same load. These relationships were confirmed by the experimental results and graphs. This experiment demonstrated how the effective spring constant changes depending on the configuration, aligning well with the theoretical predictions. Thank you for listening, and I hope this helped you to understand the physics behind series and parallel configurations.